So next we have the technology presentation on improving wind turbine gearbox reliability through offline filtration. I invite our presenter, Mr. Mark Barnes, Senior Vice President, Global Business, Gearboxes Corporation. Do we have Mr. Barnes here? Actually, there's a video presentation. Okay. So this is going to be a video presentation, and post that we have interactions with the country partners and state partners.
Hi, I'm Mark Barnes, Gearboxes Corporation, Vice President of Global Business Development. Gearboxes is a leading supplier of contamination control products, including breathers and filtration systems, to the wind market around the world. Thanks for participating in this event. Today I want to talk about how we go about improving the reliability of wind turbine gearboxes through aggressive contamination control. So we're going to talk about the factors that impact the life expectancy of gearboxes, but most importantly, we're going to talk about how we can actually control those contaminants and how to extend the life of our equipment. So the first thing we need to know is when we look at any machine in any industry, but particularly in the wind turbine industry, contamination is the leading cause of failure. There are two types of contamination that we typically deal with. The first is dirt or particle contamination, and that's typically contamination that gets in from the outside of the equipment, although inside equipment, when machines wear, the wear debris that's generated also becomes an internal contaminant. But most of the time, particle contamination is what we call ingressed, meaning it is brought in from the outside, either through a shaft seal, or through the fill port, or through new oil that's not properly decontaminated, or through the breather or the vent port. So about 82% of mechanical wear is caused by contamination, and it leads to a number of different failure modes. Those include abrasion, which is sometimes referred to as cutting wear, erosion, which is more commonly found in things like hydraulic systems where we have high flow rates and high pressure, as well as fatigue. In gearboxes that we see in wind turbine applications, fatigue is one of the leading causes of bearing failure in wind turbine gearboxes. In addition to particle contamination, the other contaminant that we are concerned about is water, and that's particularly prevalent in wind turbine applications because a lot of our installations are in coastal locations, right? So that's obviously where the prevalent winds are, and of course, being close to an ocean means that the ambient humidity in the nacelle up tower is going to be pretty high. So as that moisture enters, if the humidity inside the nacelle is very high, then the humidity inside our gearbox is also going to be pretty high, and that water can create problems such as rusting and corrosion. It does also impact fatigue life of bearings because water is actually, of course, a very poor lubricant, and it reduces the overall film strength of the oil. So controlling contaminants is critically important for achieving optimum reliability for wind turbine gearboxes. This is data that shows the life expectancy of the element bearings that we see in a gearbox relative to how much water we keep in the oil. So if we look at the water content, typically when the water level is above about 200 to 300 parts per million in a gearbox application, the oil is said to be saturated. Saturated simply means that the water is completely the oil, I should say, is completely saturated with water, and any additional moisture will be in what's called the free and emulsified phase. And as you can see from the graph, when water is in the free and emulsified phase, the life expectancy of a bearing is at or below about 75%. In fact, when you get up to 500 parts per million, which is just 0.05% by volume, the life expectancy of a bearing is below 50%. In other words, the bearing will last just half as long as it's intended to, or how it's designed. What's important about this curve is as you look at the oil becoming dry and dry, you move to the left-hand side of the curve, you can see that as we get below the saturation point, and any water that's present is just dissolved in that oil, you can see there is an exponential increase in the life expectancy of the bearing. So if we want to extend the life of our gearbox, it's really important for us to keep water levels at the left-hand side of this curve, well below the saturation point. So if we see what the impact is, that the easiest way for us to do this is actually to install a desiccant breather on our gearbox. So if you look at a standard desiccant breather, which contains silica gel, if you look at the humidity inside the oil sump, in other words, inside the gearbox, when you first install a desiccant breather, typically the moisture, the saturation point, drops to around 10%, so 10% relative humidity, which of course is well below saturation. And even though over the life of the breather, the humidity does rise a little bit inside the gearbox, provided we change that desiccant breather at the right interval, we are always going to be operating at or below 30% relative humidity. That means we're well below the saturation point, even with fluctuating ambient temperature, daytime, nighttime temperature swings. That oil is always going to be below that 30% mark. So if we look at the impact that that has on the bearing, we will find that we're working on the left-hand side of that curve. So you can see that with a desiccant breather that's operating, let's say, between 10 and 40% relative humidity inside the headspace, which means between 10 and 40% humidity in the oil, we can see that our bearing life is always greater than 100%, perhaps as much as 75 to even 100% above. So that typically will allow our bearing to last much longer. And again, it's a very inexpensive investment that we can achieve this just by installing a desiccant breather. Okay, so that's the first type of contaminant we think about. But the second contaminant that's of concern with wind turbine gearboxes is particle contamination. And when we talk about particle contamination, we're not talking about big rocks, and chunks, and grit, although that of course is a contaminant. We're talking about really, really small particles. So if we think about the size of a human hair as an example, human hair is about 50 to 70 microns in diameter. What we're talking about, the particles that cause all the damage, the dynamic clearances inside our gears and our bearings, those particles are typically less than 10 microns, right? So when we think about 10 microns, a micron, of course, is a millionth of a meter. That's a pretty abstract term. When we think about 10 microns, that's about the same size as typical allergens like dust, pollen, mold spores. When we get down to the 1 to 5 micron size range, which is really critical, particularly in our rolling element bearings, these are the same size as smoke particles, soot particles, even viruses, right? So when we think about, for example, an N95 mask, that is designed to keep very, very small virus-sized particles out of the airflow. And that's exactly what we need to achieve in order to optimize the reliability of our gearboxes. So we're going to control or try to control particles in the 1 to 10 micron size range. Let's think about the effect that that has. So the way that we measure particles in oil is to use either the ISO 4406 contamination control standard. Some people also use the NAS 1638 standard. But either way, these are scales of measurements to identify how clean or dirty the oil is. So as we look at this graph on the left-hand side, that would be considered 24, 22, 19 is considered obviously to be very, very dirty. As we transition from the left-hand side to the right-hand side of the graph, the oil is becoming sequentially cleaner. For every 1 unit scale, we go from left to right. For every change in scale, we can consider the oil as, roughly speaking, twice as clean. So as we transition, you can see that as the oil becomes cleaner and cleaner, the life expectancy both of the elements, the rolling element bearings within the gearbox, as well as the gears themselves, increase, and it's not linear again, it's an exponential increase. And that is related to the fact that the cleaner the oil, the better the reliability of that asset will be. Now, with wind turbines, of course, OEMs, gearbox OEMs have known this for a long time and have established typical cleanliness levels. Now, most of the time when I look at oil samples from wind turbine gearboxes, most of the samples I see tend to be in the 2018-15 to 18-16-13 range. So while that's certainly not as bad as it could be, optimum cleanliness, which for most wind turbine gearboxes is around a 17, 15, 12, or even a 16, 14, 11, if we can establish that level of cleanliness in a gearbox, we potentially can double the life of that gearbox. So instead of the gearbox failing at 7 to 10 years, we may be able to achieve the full 20 or 25-year design life for that gearbox. So this all goes hand in hand with keeping the oil clean. Now, of course, OEMs are very familiar with this and they understand the importance of cleanliness. The problem is that for many wind turbine gearboxes, the only protection that we have is the full flow filter. Now, many of the full flow filters that we use in wind turbine gearboxes are 10 microns. Occasionally we see 5 microns, but a lot of the filtration that we see up tower is really limited to 10 micron particles, and that's a challenge. So the obvious solution would be, well, how about we just replace that 10 micron filter with a 5 micron, or maybe replace the 5 micron with a 2.5 micron. And while in theory that seems like a really good idea, it can create some real problems. The reason is because, of course, a filter is a trade-off between oil flow and particle capture. So if you go from, let's say, a 10 micron filter to a 5 micron filter, you need to halve the size of the pores, of the holes. And what that does is it restricts the flow. So potentially going from 10 to 5 microns, it may require not just a filter upgrade, but also a housing upgrade. We may need to use a larger filter to get adequate flow so we don't starve the gearbox of lubrication. So this is not always a feasible or the most cost-effective way to achieve contamination control. The more effective way to do this is actually to supplement the full flow filtration. So accept that 5 or 10 microns is about the limit that we're ever going to be able to achieve with full flow filtration, and to upgrade by installing an offline filtration system. Now, offline filtration systems are installed, as the name would suggest, they are installed in an offline fashion. So they pull from the bottom of the sump on the gearbox, put the oil through a very fine filter. Typically, these filters are 99.9% efficient or greater at 3 microns. So we're removing those very tiny particles that create all of the problems. And typically, we're able to maintain particle counts at or below 16, 14, 11. We can do this because they are offline, so they don't impact the flow of the oil to the bearings or to the gears. It is a slow flow pulling from the oil sump back, returning to the oil sump. So over a slow process, we're polishing the fluid, and that fluid is becoming cleaner and cleaner. And the impact of that is to really drive increased reliability for the gearbox, to achieve much longer life expectancy of the gearbox, and again, potentially to achieve the full life expectancy of that, of the design life, I should say, of that gearbox. And if we look at that in terms of the number of cycles to fatigue failure, you can see that as we get to lower and lower micron ratings on our filtration, so the domain of full flow filtration with a wind turbine gearbox, again, as I said before, is typically 5 or 10 microns or greater. That's typically going to give you about 7 million cycles of fatigue life. Whereas if we reduce our micron rating through offline filtration, we could potentially get 14 to 16 million fatigue cycles before that bearing will fail. So you can see the impact is approximately an expectation of doubling the life of the gearbox. And of course, from a financial perspective, if you can get twice the life out of a gearbox, that's a very significant cost savings. So to summarize, contamination is one of the leading causes of failure in wind turbine gearboxes. We need to consider the sources of contamination, most of which are going to get in from the outside. So in other words, ingressed contamination from the ambient environment. The two contaminants we have to think about are particles and moisture. The most effective way to control moisture is to control the humidity of the air that enters the gearbox during normal operation, normal what we call thermal siphoning, so daytime, nighttime heating. And the best way to do that is to install a desiccant breather to control headspace humidity. With particle contamination, we want to make sure that our full flow filtration is in good condition and that we are using the most effective filter we can. But by supplementing the full flow filter with an offline filter, we can really look to extend the life of our gearbox and to extend the life of the asset overall. So my encouragement to you is do some research, go ahead and look at ways to install supplemental filtration, talk to the Descase people that are at the Wind Turbine conference there, and let's see how we can support your reliability efforts through upgrading your filtration and contamination control. So thank you for your participation. We hope you have a good conference.
So thank you to Mr. Barnes for his presentation. And